Okay, so the fundamental theorem of calculus tells us, if you remember, that in order to take the integral, or to evaluate the integral of small f of x dx, one just has to find an antiderivative, capital F, and evaluate it at the upper and lower limits of your integral, and you will get the exact value of this integral. So this is why, for us, anti-differentiation is going to be a big deal, right? Because that's exactly what this theorem says, that in order to evaluate any of these integrals, you basically just need to ask the question, what function has derivative small f of x? And while we had that list of integrals before, for instance, we know that integral of cosine x dx is equal to sine x plus c. Right? So this is the general family of antiderivatives of cosine x, because any function of this form, when you take the derivative, will give you cosine back. What we will be concerned with moving forward is, well, what do we do if the integral that you have, well, does not fall into one of those standard forms that you saw in that list? Polynomials, sine, cosine, and so on. And so let's start with a relatively simple example here. Evaluate the integral 2x times cosine of x squared dx. And remember, what we want here is the following. We want to find a function such that when you differentiate that function, it gives you 2x times cosine of x squared. So what I'll do right now is just give you time to work on this problem yourself. So pause the video and see if you can find what this antiderivative is for this function. Okay, so did you figure it out? Did you even pause the video or not? Well, that's okay. I'll tell you the answer anyway. But, maybe I'll do this. If I were to rewrite my function as cosine of x squared times 2x instead, maybe now this is something that you recognize, because it strangely looks like something that might have come out of an application of the chain rule. Right, so remember what the chain rule says. If you have a composition of two functions, f of g of x, and you differentiate that composition, then its derivative is capital F prime of g of x times g prime of x. That looks very similar to what we have right now, right? Especially observing here that x squared, which is the term inside your cosine, when you take its derivative, will give you 2x, which is that term outside. And so maybe putting sine of x squared here works. Right? So sine would have given you cosine when you take its derivative. But clearly it's not just cosine here. It's sine of x squared. And now it's actually easy to show that this is correct. Because when you take the derivative of sine of x squared, then again, exactly by the chain rule here, you get cosine of x squared times 2x. And so this gives us a way in order to systematically evaluate integrals like this, right? By seeing them as just the reverse operation of the chain rule. In fact, if you can write your integrand, right, the function inside your integral, if you can express it in this form, where you see a bunch of g of x terms inside, and it's multiplied outside by a single g prime of x term, then you know that it can be expressed as the derivative of a composition with that g of x inside. Okay, let me show you what I mean. Going back to the same integral here. Integral of 2x cosine of x squared dx. Well, remember first that the chain rule can be written using Leibniz notation in this manner. dy dx equals dy du times du dx, right? Where y equals f of g of x and u equals g of x, right? So it's whatever the inner function is. So that question of finding what this gx term is and using it to go back is the same question as, well, what is my u function? And in this case, I'm going to say, well, I see an x squared in there, and then I see a 2x outside, which is exactly the derivative of that 2x. So if I write it this way, cosine of x squared times 2x dx, I can now say, if u equals x squared, then du dx is equal to 2x, or abusing my notation slightly here, I can now say du, so that's a u, that's not a y, that's u, du is equal to 2x dx. Therefore, this allows me to rewrite my integral just in terms of u, right? So this x squared here becomes just u, that's my u, and 2x dx outside is now, the entire thing becomes just du. And now this is nice. Well, why is it nice? Because it's now part of that huge table of integrals that you saw last time, or that's in your textbook. Cosine of u, its antiderivative, you're taking it with respect to u, it's just sine of u plus c. And now expressing everything back in terms of x again, now we can write this as sine of x squared plus c. Right? And that's again exactly what we came up with up here. And so here I just want to state what we call the substitution rule, right, in generality here, saying that, again, if you can recognize that your integral, or your integrand, can be expressed using this g of x terms inside, and you have a single g prime of x term outside, then you can make the substitution u equals g of x, which in turn gives you du equals g prime of x dx, again using that slight abuse of notation that we did last slide, in order to write your entire integral just in terms of u, hopefully making it into a simpler expression to evaluate. So let's end with an example here, something that you may want to try yourselves as well. How about the integral of 2x plus 1 raised to the 10th power dx? Again, you may want to pause the video here and try thinking about this yourself first. Okay, so what should we do? Well, using this idea that we did in substitution, it kind of looks like you have an inner function here, right? You're raising something to the 10th power, and it's not just x, right? It's another function inside that's 2x plus 1. And so if we set u to be equal to 2x plus 1, does that actually get us anywhere? Well, let's see. du is what? Well, du dx, the derivative of u with respect to x, is 2. So du is 2 times dx. Okay, but wait. We don't have 2 times dx here, right? We just have dx. That's no problem at all in this case, actually, because 2 is just a number, it's just a constant. So why don't we go ahead and multiply by 2 and divide by 2 at the same time, so that we don't change whatever the integral is, essentially forcing your integrand to have that g prime of x term dx, thus allowing us to make this exact substitution by taking 2x plus 1 and writing it as simply u. 2 times dx now becomes just du. And you still have that 2 in the denominator here, so we're multiplying by 1/2. Well, and now that's part of your table of integrals, right? It's just u to the 10th power. So it's a monomial. Power goes up by 1 when you take the integral, and you divide by the new power as well. The 1/2 is still there because it's a constant, and don't forget to add plus c. Finally, writing everything in terms of x, this is now 2x plus 1 raised to the 11th power over 22 plus c. And I'll end with a tip here, is that you can always check your work when you're integrating. Take whatever function that is that you ended up with, differentiate. Okay, so how do we differentiate? So it's the chain rule as expected, right? Because we use the substitution rule to integrate. So 11 goes down, you multiply by 2x plus 1, power goes down by 1, so it's now 10. Chain rule says you multiply by 2, because it's the derivative of the inside function. And then over 22, that's still there. And 11 and 2 cancel with 22, leaving you with the correct function that you started with.